review the equation sheet for this lecture. The equation sheet, as we can see, has got a number of equations on computation of, say, different parameters in machining, and those include the first equation up here, that one, which is the well-known equation for material removal rate. And this is the one that we already had in the previous two sessions as well. Material removal rate is indeed important in any machining operation because it is an indication of the efficiency of the machining process. As material removal rate is higher, it means that we are performing a more efficient process. And it can be computed if we have the values of cutting speed, feed, and depth of cut at hand. Well, the next equation on the equation sheet gives us the chip ratio. If we have the depth of cut, TO divided by chip thickness, that is TC. If we take a look at this figure down here, then we'll see what these parameters are. This is TO, which is indeed the actual depth of cut before cutting, and TC up here is the thickness of the generated chip after it is separated from the workpiece material. Always TC is larger than T0. And then we have got another equation here which is relating the parameter phi. What is phi? Phi is the shear plane angle. Relates shear plane angle to the chip ratio, this one, and also the rake angle. Rake angle alpha and also shear plane angle phi play a very important role in any machining operation. Let's take a look at this orthogonal representation of the machining operation down here to see what these are. This is the shear plane angle phi, this one. As you can see, it is the angle between the plane at which shear is happening with and also the reference plane, which is the horizontal plane. So the angle between these two is referred to as shear plane angle, and this angle is playing a very important role in the machining operation. That is, as this value is higher, we are performing a better machining operation. So we've got to try to increase this value, the value of phi, as much as possible. And this is a function of some parameters, including the rake angle alpha, which is shown right here. The rake angle is the angle between the top face of the cutting edge and also the reference plane. As this is greater, it will give us a higher value of phi. And this equation here is relating phi to the chip ratio R and also the rake angle alpha. Another equation down here, which is giving us the shear strain. And this is a function of both phi and also alpha. As this is greater, it means that there is more deformation taking place in the chip itself while it is being separated from the workpiece material. So it means that if we are having a higher value of phi, of gamma, which is this parameter, then we are deforming the chip more than what is really necessary. So a lower value of gamma would give us a more efficient machining operation. Moving on to the next series of equations, next slide, the rest of the equations, a number of equations that represent different forces that are generated in a typical machining operation. This one up here is giving us this parameter here is mu, which is referred to as the coefficient of friction, and is also a function of beta. And beta is the friction angle. What is beta? If we take a look down here to this figure, we can see what beta is. Beta is the angle between the normal force to friction and also the resultant force of friction. The angle in between is beta. And then there is another equation here which is giving us the strength, the shear strength of the material S, which is obtained when we divide shear force Fs by the area of shear As. If we take a look down here, we can see where shear force applies. The shear force is the force which is applied on the shear plane. This is right here, shear plane. When material is subjected to actual separation, this cutting tool is applying a force, and on this plane, material slippage is happening. So this is referred to as the shear plane, and it has got two dimensions. This is the dimension that we can see. The other dimension, which is representing the width of the cut, is normal to the board, so we don't see it, and it is represented by parameter W, which is the width of cut. Another equation here is the one which is actually representing the area of shear, and we can see the depth of cut, or W, is taken into consideration here. So the area of shear which is subjected to the slippage of the material can be computed by making this use of this equation. Again, we've got W, width of cut, depth of cut, T0, and also the sine of angle phi. And we know what angle phi is, the shear plane angle, this angle right here. Okay, we've got four equations, a set of four equations which represent friction force, normal force to friction, shear force, and normal force to shear. All these forces are shown in this figure down here. This is F, this is normal force to friction, this is friction force, this is normal force to friction, this is Fs, shear force, and this is the normal force to shear. So all these forces are defined here, and these are related to cutting force Fc and also thrust force Ft. Cutting force and thrust force are not shown in this figure. However, thrust force is a force which is vertical. Right here, down here, it is an upward force. And then we've got thrust force, which is a force along the surface that is being produced. So this is cutting force, and this is the direction of thrust force. I can just show it by some lines. If there is a force in this direction which is being applied to the tip of the cutting tool, this is thrust force, and this is actually Fc, which is the cutting force. These two cutting forces can be measured directly if we have a dynamometer in place during the machining operation. So Fc and Ft can be directly measured during the machining process. However, other forces that include Fs, Fn, F, and N cannot be directly measured when the machining process is in progress. So a scientist who is called Merchant, his name is Merchant, he has developed these equations relating these forces to one another, and he has also introduced this very useful equation down here, which is also known as the Merchant equation. Well, if we have the values of Fc and Ft, which can be directly measured, and we have the value of alpha, which is the rake angle is a property of the cutting tool. So this is something that we know when we have selected the cutting tool, then we can easily estimate the magnitude of F and also the magnitude of N. Similarly, if we have the values of Fc and Ft at hand, and if we know the value of phi, which is this angle here, then we can estimate Fs and also Fn. That's the story behind all this. And also he has developed a force diagram. Merchant has developed a force diagram here, which is relating forces of Ft and Fc to the other forces, which include Fn, Fs, F, and N, if we have the magnitude of the resultant force here. So by making use of this diagram, we can relate these forces to one another by making use of some trigonometric equations that we can write by making use of this force diagram. And the Merchant equation, the one that is in the square here, is relating the shear plane angle phi to the rake angle alpha and also to the friction angle beta. This is the equation that Merchant has developed. And this is a very useful equation in the theory of machining. And the next group of equations are the ones that are used in order to estimate the power of cutting, the gross power for cutting, specific energy for cutting, mean temperature rise, and also the tool chip interface temperature T, which is a function of cutting speed. So this group of equations are useful when we want to compute the power that is needed for performing the cutting operation, and also the temperature that is generated as a result of friction between the cutting tool and also the workpiece. Right here, there is a friction, a large amount of friction between the chip, which is separated from the workpiece, and the top face or the rake face of the cutting tool. And this friction generates a lot of heat, making the chip and cutting tool as well as the workpiece really hot. So we've got to reduce this friction as much as possible, and that's one of the reasons why some sort of lubrication are used. Lubrications are used in the machining operations. One of the functions of the lubricant is to lower the friction between the chip and also the cutting tool. Okay, now let's move on to the first problem of the tutorial session. This is showing an orthogonal cutting operation, orthogonal or 2D representation of the cutting process. In an orthogonal cutting, the tool has a rake angle of 15 degrees. Let me show you the figure. This is the 2D representation of the cutting process. The rake angle, which is this angle, the angle between the top face of the cutting tool and the reference plane, or alpha, is equal to 15 degrees. The chip thickness before the cut, this one, chip thickness before cut or depth of cut, is T0, is equal to 0.3 mm, and the cut cycle yields a deformed chip thickness of this much, 0.65 mm. So the thickness of the chip after it is separated from the workpiece is 0.65 millimeters. We are to compute or to calculate the shear plane angle. Shear plane angle is this angle here, is this angle right here, phi, and also the shear strain for the operation. Okay, now let's take a look at the equation sheet to see which one of the equations is the one that is going to help us in this. Indeed, we have got this equation here, which is helping us in order to compute the chip ratio, and also we have got another equation helping us to compute the value of phi if we have the value of the rake angle and r at hand. And eventually this last equation is the one which is helping us in order to compute shear strain if we have the values of phi and rake angle, phi and alpha at hand. So we take these equations from the equation sheet and return to the statement of the problem, this one. Okay, now we are provided with alpha, with T0, and also with TC. What we need to do is to compute phi and gamma. In order to do that, first we compute the chip ratio having T0 and also TC at hand. We compute the value of R, and then we make use of the other equation which relates phi to the say rake angle and also chip ratio, and solve the equation for phi. Once we revise the equation for phi, we have the values of R and also alpha at hand, so we can easily compute the value of phi, which is the angle of the shear plane. So that comes to 26.85. And then the last thing that we've got to compute is the shear strain. Again, we take the equation from the equation sheet for the shear strain, and substituting the values of phi and also gamma, which are both available now, we do the computation of this value, which is 2.185. So we take a note of what we have obtained from here. We have got say a shear plane angle of 26.85 and we have got a strain of 2.185 from this problem. Is there any questions? Okay. If there is no question, then we move on to the next problem, which is indeed the continuation of the same problem. Let's see what it is asking us. Please keep in mind that we had a rake angle of 15, and also we had a chip thickness of 0.65 in here, and the value of beta is not given because it's not needed. Now let's move on to the next problem. Problem 2. What is this problem asking us to do? In the previous problem, suppose that the rake angle were changed to 0. So it was 15. Now we are supposing that it is changing to 0. What it means is that we are making use of a different cutting tool with a rake angle of 0 instead of the one that we had used before, and that had a rake angle of 15. We want to see how a change of rake angle will change everything indeed. Assuming that the friction angle remains the same. Friction angle or beta remains the same. It wasn't given in the previous problem, but we are considering that the rake angle will not change. Determine the shear plane angle, the chip thickness, shear plane angle or phi is to be computed. The shear plane angle or phi, the new value of phi according to the new rake angle is to be computed. The chip thickness, TC, is to be computed, as well as the shear strain. So we already computed shear plane angle and also shear strain, and the chip thickness was given in the previous problem. Now it is not given and it will change because the rake angle changes. Okay, in order to do this problem, we've got to take a look at the equation sheet again. Okay, let's take a look at the equation sheet to see which one of the equations is the one that will be useful in doing this problem. In order to compute, say, the value of phi, in order to compute the value of phi, we can make use of either this equation where phi can be computed, or there is another equation in the next slide, that one, the Merchant equation. The Merchant equation, which is this equation. So we take this equation from the equation sheet, and also we take the other three equations from this equation. We take these three equations from here to see if these help us in order to do this problem. Three equations from here, from this slide, and also one equation from here. We take these equations and return to the statement of the problem here. Okay. Now let's see what is given. We are provided with T0, TC indeed is not valid anymore. What we had was for the previous problem. And now alpha is changes to 0 and beta remains the same as it was in the previous problem. And we are to compute phi, new TC, and also gamma. In order to do this problem, we make use of the Merchant equation. And in order to make use of the Merchant equation, we need the value of, if we want to compute the value of phi, we need to have the value of alpha and also beta at hand. Alpha is already given up here. Up here, we've got it. It's now, its value is 0 in problem 2. The value of beta is not given. It's not given in this problem. It wasn't given in the previous problem as well. However, we have been told that the value of beta or friction angle doesn't change. It remains the same as it was in the previous problem. If we have the values of alpha and beta at hand, we can easily compute the value of phi, the new value of phi. What do we do now? Well, as we know that the value of beta remains the same, we return to the values given in the previous problem and compute the value of beta on the basis of what was given in the previous problem. If we make use of this same equation here, and substitute the value of phi that we had for the previous problem, and the value of beta alpha that we had for the previous problem, then we can get the value of beta again for the previous problem, which was problem 1. And we know that this value of beta remains the same for the second problem. So we do it this way. On the basis of the problem 1, we compute the value of beta. In the first problem, we had the value of alpha that was equal to 15. And the value of phi was computed, which was 26.85. So this gives us the value of beta for problem 1. And that is 51.3 degrees. This is the friction angle. And then once we have this at hand, we know that this same value is applicable to the second problem. Okay, now we have got the value that can be used for doing the second problem. Now, again, we make use of this same equation, Merchant equation. We make use of this same equation. This time we substitute the value of new value of alpha and the value of beta, which is the same. Then we can compute the shear plane angle for the second problem. Does it make sense? If we compute the value of beta on the basis of what was given in the previous problem, and then it remains the same, so we substitute the new value of the rake angle alpha and the value of to compute the value or new value of phi. So we can do it this way, and we'll do it. Okay, this is the statement of the problem. Let's see how it changes. Now the rake angle right here is 0, as you can see. The rake angle is 0, and in the previous problem it had a non-zero value. What are the effects of it? When it changes, this TC will increase significantly, and the value of also alpha will be reduced. Now we do the computation. We make use of the Merchant equation, knowing the value of beta remains the same, and the new value of rake angle is 0. Now it gives us a different value for plane angle, and that is for the shear plane angle, and that is 19.35. So now this is a different value. It was 26 point something in the previous problem. Now because of a change in the say value of rake angle, the shear plane angle also changes to 19.35, and this is less than what we had before. And then in order to compute the value of the TC, new value of TC, what we need to do is to form a triangle, the triangle right here, this triangle. Now we have got the value of this angle, and we know TO, which hasn't changed. If we have this side and this angle, then we can easily make use of the trigonometry and compute the value of TC. And we do it. Now we compute the new value of TC, and it is this much. And this was 0.65 before. So as we can see, the value of phi is decreased from 26 point something to 19.35, and the value of TC is has increased from 0.65 to 0.85. And the only remaining parameter is say the shear strain. Now we make use of the equation, substitute the new values of phi and also gamma, and get it computed, and it comes to 3.199. And again, this value is greater than what we had for the previous problem. It was 2 point something in the previous problem, now it is 3 point something in the new problem. The only thing that is different from this problem compared with the previous problem is the rake angle. The rake angle was reduced from 15 to 0, and now we can see the shear plane angle is less, the chip thickness is more, and also the shear strain is more. And this is a less desirable situation considering compared to what we had before. As this value is higher, we will have a more efficient operation. Now this is less. As a result, TC thickness of the chip will increase. As a result, or as a consequence, the amount of deformation of the chip will be greater. And it increases from 2 point something to 3 point something. So it means that having a larger rectangle results in a more efficient and more effective cutting operation. So these two problems show us the difference in changing the rectangle and also the change of shear plane angle. Is there any question? No questions. Okay, moving on to the next problem. In the next problem, we will be making use of the force diagram for doing the problem. Okay, problem 3. Let's see what we are asked to do. Low carbon steel is generally considered as an easy to machine steel. Low carbon steel is a mild steel and it is easy to machine say material. Having a total strength of this much and the shear strength of the given value is cut in a turning operation. So the type of the operation is turning. With a cutting speed of this much, V is given, feed is also given. Depth of cut is another parameter that is given to us. What is the rectangle? The rectangle is 5 degrees. 5 degrees of rectangle is still better than a rectangle of 0. As this is greater, it will be easier for us to proceed with the cutting operation. The resulting chip ratio R is given. Instead of T0 and TC, this time we are provided with the chip ratio, which is R. Using the orthogonal model, an approximation of turning determine the shear plane angle or phi. So again, we've got to compute the shear plane angle. As mentioned, shear plane angle is a deciding factor or parameter in any machining operation. So it is a very important angle. And then the shear force Fs is also to be computed. And in part C, we've got to compute cutting force Fc and thrust force Ft. Okay, let us summarize what is provided. We are provided with the type of operation which is turning. Feed is given, depth of cut is given, rectangle, chip ratio, the type of the material which is low carbon steel, tensile strength, shear strength, cutting speed, and what we need to compute is shear plane angle or phi, shear force or Fs, cutting force Fc, and also thrust force Ft. These are the ones to be computed in this problem. Okay, now we need to take a look at the equation sheet to see what are the equations that we need in order to get this done. Let's take a look at the equation sheet. In the equation sheet, well, this is the equation sheet. In the equation sheet, we've got to take a number of equations out from the equation sheet in order to get this done. For this problem, we will be making use of this equation here. So we take this one out from the equation sheet. Any other equation on this sheet that will be useful? I don't think any other one will be useful. This is the one that is making us able to compute phi on the basis of R, which is given, and also the rectangle. These are both given, so we can easily make use of this equation to compute the shear plane angle. Let's move on to the next slide. Which one of the equations from this sheet, slide should we take out? Well, we need to compute shear strength, so we take this equation out from here, as well as the shear, the area of the shear plane. We take this equation out as well, these two. Plus, we are to compute the shear force. The shear force, which can be computed if we make use of this equation up here, we can compute Fs if we have the values of As and shear strength at hand. This is already given. This one is not given, so we make use of equation 28, this one, in order to compute As. So we take these two equations from the equation sheet, plus I will be taking this equation, that is merchant equation, as well. So we take these three equations from the equation sheet in order to be able to do the problem. Do we need any other equations? We need to compute Fc. Don't forget that we need to compute Fc and also Ft. So we are taking these two equations from the equation sheet as well. Okay, so 1, 2, 3, 4, 5 equations from here plus one equation from the previous step. We take the 6 equations from the equation sheet. Now let's return to the statement of the problem, this one. Okay, first we compute phi, which is the shear plane angle. If we make use of the equation that we have taken from the first slide, we have the values of R and alpha. So we simply substitute all the values, which is giving us the value of shear plane angle, and that is 25 degrees. It's easy, straightforward, so we substitute the values and get this computed. And the next thing that we need to compute is the shear force, Fs. How do we compute shear force? Indeed, in order to compute shear force, we make use of this equation here, and as I mentioned before, Fs is included in this, S is given, the area of shear plane is not. So first we compute the area of the shear plane. Width of cut is given, which is indeed equal to feet. In turning operations, a width of cut is represented by W. In milling operation, it is represented by W itself. But in turning, W is can be substituted by feet, and the value of feet is also given, that is 0.2. Well, T0 is given, and also phi is just computed. We just had it computed. So we can easily compute area of shear, and when we have the area of shear computed and S, which is shear strength, and that is given, we compute the value of shear force. So far, so good. And then after we have this computed, what else do we need to compute? This is computed. This is also computed. What else is to be computed is cutting force and thrust force. And we have taken two equations from the equation sheet, making us able to compute FC and FT. Let's take a second look at the equation sheet. This one. Well, let's take a second look at this sheet here. As we can see, we have got two equations here. This equation is relating Fs, which is not computed, to Fc and Ft, but there are two unknowns in this equation. We have phi available, we have it computed, we have Fs computed, but we have Fc and Ft still as unknowns. Let's take a look at this equation down here. In this equation, we have phi available, Ft is not available, Fc is not available, Fn, which is also not available. So we have got another equation with three unknowns. How do we do this problem? If there is a way of computation of Fn, because we have Fs available, if we can somehow compute Fn on the basis of what we have at hand, then we can form two equations and two unknowns right here. This is already given. This is already computed. This is computed. This is computed. So this one is computed. This one is computed. And we have got this one as unknown. If we can somehow compute Fn, then we can form two equations and two unknowns, two simultaneous equations. And there will be two unknowns in these equations. Then we can solve the problem. So let's focus on computation of Fn. If we can somehow compute Fn, then we will be able to do the problem. Okay. Back to the problem. Okay. This one, we had Fs computed. Now let's take a look at the force diagram. This force diagram is something that we had in the lecture. Let's take a look at this triangle in the force diagram, this one. If we take this one out, which is giving us this, Fs is something that is computed. If we have this angle computed, then we can compute the other side of the triangle, which is giving us Fn. However, we don't have this angle at hand, but we know the value of phi and we know the value of alpha. If we can compute the value of beta, then we will have this angle available, and then eventually we can also compute Fn. In order to get this done, what we need to do is to make use of the equation of merchant equation, this equation. If we make use of this equation, having at hand the value of phi and also alpha, we already know the value of alpha, we have just computed the value of phi, then we can also work out beta. So we compute the value of beta. Once we have the value of beta computed, then we have beta, alpha, and phi all available. Then it is possible for us to write a tan equation, the tan of this angle, which is equal to Fn divided by Fs. And we do it that way. And we solve the problem for Fn. Now we have this angle, so we can compute its tan. We have Fs available. From this, we can compute the value of Fn. So by making use of the force diagram, we took this triangle out and we computed the value of Fn. Now we are just one step away from computation of Fc and Ft. Now we develop two simultaneous equations. Okay, Fs is computed, Fn is computed. We know the value of phi. So the only two unknown parameters are Ft and Fc. And of course, we can solve these two equations as simultaneous equations, giving us the values of, say, Fc and Ft, which can be computed easily. Okay. Any questions on this? Okay. That's the way of making use of the force diagram in order to get these computed. Okay. Any questions? No questions. Okay, please do these problems in your own time and make sure that you are making yourself familiar with the force diagram and how to make use of the force diagram in order to relate different forces to one another. There are two more problems. On computation of, say, machining power. And I am leaving those two problems to you to be done at home. All you need to do is to make use of the equations on the equation sheet, substitute the right values, and get the values of the power computed. And if there is no questions, that's all for this session. Any questions before I conclude the session?